Let's start. So, I'm Avi Mendelson, for those who don't know who I am. My part in this class is mainly the architecture part and more practical aspects of the system. And actually, we will have mainly 2 sessions on more architecture. And this section is more an introduction to systems. And I want to devote, first of all, you have some of the material you have, I think that this is in class 1, I'm not sure, which is the previous year's introduction. So this time I want to focus on what I call conceptions and misconceptions about working on systems, and I try to do it quite fast, but I need it in order to be able, next 2 classes, actually to talk more about fundamental things, and the question will be why we are doing it. For example, next class we are going to talk about quantization, and quantization meaning that we are going to use, instead of integers, we are going to use a small number of bits in order to represent the numbers. And the question, okay, so why you are doing it? What you try to gain? Why to complicate the system? Machine learning is complicated enough. So we need to understand some of the background. So this time I'll go over mainly a few very basic concepts, and please interrupt me if you have questions, because again, it's not very technical, but I think that for many of you, it will give a different way of looking on systems. So usually the focus of the course is on efficient implementation of machine learning, but the notion of efficient execution is not always identical to the notion of complexity, because in computer science, usually you have a course on complexity and you discuss the complexity of algorithms, and at some point students start, not only students, people start to confuse between efficiency and complexity, for example. So in this presentation, I'll try to clean up some of this notion and to talk more about what does it mean from the system point of view to run an efficient algorithm. So first question is, what is the difference between research and engineering? And again, it goes to the very basic observation that in computer science, we talk about upper bound, lower bound, it is NP hard, NP complete, etc., etc., etc. In engineering, we intend to achieve similar goals, but under constraints. And this is interesting. For example, do you know, if you just go to department store in US or anywhere and you look for example for an inexpensive cellular phone, not to the fancy one, but an inexpensive cellular phone, so you find out that most of them has the same price. Surprise, surprise, why all of them has the same price? So the reasoning is nothing to do with technology. And by the way, the amount of money, what they call the margin, the amount of money that they are gaining out of this one is vary between the different companies. Different companies have different margins. But all of them sell you for the same price. So what is the reasoning around it? Does anybody knows? What is the reasoning? Yeah, first of all, you try to achieve the maximum price that you can. But in many gadgets, not all of them, but in many gadgets, the criteria is something which is really, really funny. They goes and do some poll around all the customers. What is the maximum money that a white man will to spend without calling his wife and ask for a permission? This is the question. because they know that as soon as he will call back home and ask, oh, can I spend $500 for this nice phone? Let's think about it. So this is the criteria if you want to say something that somebody buy not as a fancy, but just as a gadget for the by this. So this is what they ask. It has nothing to do with technology. So now you have the price, and from this price you go backward. And in this, when you go backward to put all the margins, so you say, okay, you need to design for me a chip that this chip will cost $5, $10. And this is the constraint that you have. Now you have to get the best for the money or for the budget. This goes the same for energy and for everything. So even in the computer science, we are talking what is the best that we can achieve. Usually when we are talking about system, we are talking about what is the best that we can achieve under limitation or other constraints. So for example, we all study, and I hope that all know about cache memory, L1 cache, L2 cache, L3 cache, etc., etc. If you actually understand what it's all about, is you try to aim to achieve the fastest average access time to memory, given known either cost or area budget. So if you work for Intel, for example, so they will tell you, you have this much square millimeters that you can spend for on die cache. It's up to you to partition it in any way. The marketing or the manager really don't care about what is the internal partition. So you need to find what is the best parameters if to take it is one level or many multi-levels, and how to define it. But again, you have the constraint, you need to fit into this constraint. Now, when we talk about deep learning, so many times you try to achieve the best implementation assuming some level of accuracy. What does it mean? It gives you a camera and say this camera will be used for security, for example, so I need to have 99% of accuracy. Or this will be a street camera, so 85% approximately is good enough. So you start with the accuracy, and now you look for the best algorithm. Now for this algorithm, you look for the best implementation. For example, this best implementation can be minimum power consumption if it is battery operated. Or it can be minimum energy for other reason, or it can be minimum cost of design. But these are the parameters. Most of the time you start with the accuracy. So it's not that you try to achieve the best accuracy. You know what is the level of accuracy, and now you look what is the best algorithm that you want to fit inside. Same goes for you want the best accuracy given some parameters such as power, etc. So you find out that there are companies that right now, for IoTs, for example, small devices, so they have quite fancy algorithm that can be implemented using a very inexpensive CPUs that consume very little power. Just for example, there is some chip of a company that belongs to Alibaba that for face recognition and so on gives you a chip that consumes 200 milliwatt. Just to compare, a GPU usually use something like 200 watts. And do almost the same work in terms of recognizing, etc. So the question is how to implement something so complicated on something very similar. So the engineering point, and in my part at least, we will talk about the engineering parts, not about the theoretical and algorithms. So we try to find many ways to implement something inexpensively. And inexpensively can be, for example, to use very small number of bits, because now you need less operations and you can consume less power, you need less communication, etc. So you reduce all the power cost of the system. So again, if you just talk about the algorithm, there is no sense to do things like quantization, binarization, and all these tricks. But if you want to implement it in a very, very inexpensive way, this is the only way to go. So this is something which is not trivial to many students. That all the time we talk about upper bound, etc., because we don't like to get better performance. We want to get better power consumption, for example, or less area, but still keeping maximum or the same level of accuracy. So we already talked about it, but just to mention complexity versus efficiency. Usually when we talk about complexity, so complexity, the real meaning of complexity, what is the sensitivity of the algorithm to, for example, the input size. When we say that something is O of n, it means that it grows as the size of the input grows linearly. If you say that it is O of n squared, so it is going exponential, etc., or polynomially. But when we talk about efficiency, we are talking about usually if I want to implement this algorithm, how efficient it runs. But this is totally different. For example, just two algorithms. One goes, I go from 0 to 1k and do I for some, sorry, one algorithm will do some summation over a column, the other will do the summation over the rows. The performance of these two lines is dramatically different. Not just a small factor, it can be something like 10 times or maybe even 15 times slower. Because when you access the information row-wise, so each time that you access data, it brings from the cache from the main memory, it brings the entire cache line. So whenever you access one element, you get for free all the rest. When you access it column-wise, so each time you need to bring it from the DRAM. Now, assume that, and these are approximately the number, accessing the cache memory course, you assume 1 cycle. By the way, it is 3 cycles, but because of pipeline, so actually it is like 1 cycle. And accessing the DRAM depends on your machine. It can be, in Intel, it's around 400 to 500 cycles. In NVIDIA, or GPUs that we'll study, it is around 1,000 cycles. So the difference is between 1 and 1,000. Huge difference. But from the complexity, it is the same. The complexity of implemented column-wise or row-wise is just the same. Because in the complexity, we are talking about the sensitivity. If I will take instead of 1K, 1 meg, does it go linearly or does it go exponentially or polynomially? But we don't care how much this the baseline really costs. When we talk about efficiency, this is extremely important, all these details. What does it also mean? That in order to understand performance, and particularly for machine learning, many times we need to understand the details of the machine that we will choose or that we need to use because the company bought it, etc. So for the algorithm part, many times you don't care, but when you try to really implement it and get real results, there is no other way but understanding at least the basic architecture that you work on, what are the advantage, what are the disadvantage, etc. So we will not go very deep into this aspect, but for those of you that want to focus or at least to do more exercises in order to really be able to run something very efficiently, so we will propose some project on it, and come approach me and we can talk about also research in this area. But anyhow, the rest of the, at least, we will have at least another 2 or 3 classes that will talk about different architectures, what are the advantage, disadvantage, etc. So, few other design consideration. Before I was in academia and then I moved to the industry for many years. Right now I am back, but when I was in the academia, I never thought about things like the stability, how easy or hard is to test your system, or verification, or verification here, but formal verification, or ease of implementation, time to market, cost and cost of ownership of chips. All these parts are very, very important if you want to do something practical in the practical world, and not just to write a paper, which are very important but serve a totally different purpose. So many times you need to sacrifice, for example, accuracy, or you need to sacrifice even cost in order to develop your algorithm in a very fast way. So many times people say, if I will not use this, for example, Café or PyTorch or one of these environment, I can implement it much, much more efficient. Yeah, but it will take me another half a year. So in practice, you will not spend the time. In research, yes, it's very important to understand the differences, but in practice, you need to take into consideration also this parameter. Well, something also which is very important, you never start developing a real system from scratch. You always use existing libraries, previous projects, etc. So to be able to integrate or to build your system out of existing components is very, very important. Going back to machine learning, the problem is that in machine learning, you start with a component, so one component is written using Café, the other is using PyTorch, the other is using a TensorFlow, and maybe for a very good reason. But each one uses its own or her own favorite environment, so how you can combine them. So a very important aspect or very important work is something that they call ONNX. And ONNX is an environment that tries to take models which are built for a different environment, translate them into a common IR intermediate representation, and then to produce it again using another environment. And most of the time it works very good. So another tool which can be very interesting for you is using something like ONNX in order to take something that was developed in one environment and move it to another. Now, for example, why it is so important? Because you can develop something that can run on the CPU, or that can run on the GPU, or that can run on FPGA. Not all the environments support it uniformly. So you can develop something that originally was A for GPU, and now take it and compile it for some ASIC or for some other environment by using this tool. This is very, very important and very interesting to see how it works. Last point that I want to mention, again, this is extremely important, that in the past, usually when we build about performance, we spoke about instruction per cycle, floating point per instruction. We talk about the CPU. Because this was the most important part in the system. The world is changing. In the next slide, I explain why. But modern processors are very, very sensitive to power, and power equal performance in some sense. And I will not go into all the equation, but just to give you the notion, the power that you consume is some activity factor multiplied by capacitor. You can assume that this is a constant, but this is a voltage square frequency. Now, usually since the voltage and frequency depends on each other, which means that when you grow up or down the voltage and frequency, you change both of them. So usually the delta power is approximated by delta frequency over 2.5. So this is a good approximation. Which means that if I just assume that frequency equal performance, so suppose that I want to double my performance. One option is to double the frequency, so I'll get to double the performance. In this case, because this is f to the power of 3, so it is something between 6 times to 8 times more performance. On the other hand, if I will just take 2 models, I will increase it only by 2. So if power is important, so usually the idea of increasing frequency is not a good idea. It costs you too much power. Now this is very important because many times we have the trade-off to get the same performance, for example, to improve your algorithm. Instead of increase the frequency, we need to be aware of this factor. But more than that, this is a graph that was produced, I think, only 2 or 3 years back. Actually, 2014, a little bit earlier. And shows that today, if I just try the energy to do some add operations, so for 8-bit, it costs me 0.03 picojoule. For 32-byte floating point add, it is 0.9 picojoule. But on the other hand, to read 32 bytes, which is a small cache line, usually cache lines are much larger today, it costs me 640 picojoule. So just look on the ratio between 640 and 0.9, which means that in real life today, the energy that I need in order to transfer data from DRAM to the core costs me almost 1,000 times or 800 times more than to compute the algorithm on this data that I move, which actually cause a major rethinking in designing of new systems. Because if in the past we mainly talk about optimizing the code, you will see that major part of modern machine learning algorithms is how to reduce the memory transfer. Going back to using quantization or less number of bits, but also we have techniques to do compression. So we try to move less information from the memory inside or for any information to use it more times, etc., etc. So we are using things which are called pruning, because you will see now, I don't know if you spoke about it or not all the bits has the same contribution to the algorithm. So if you have bits that doesn't have contribution, so maybe you don't need to transfer it. Maybe you can eliminate them. So now much of the thinking is not just the computation, how many computations you are doing, but also how much information you need to transfer from different points. And this is totally way of thinking about optimization in general, something that was never exist, let's say 5 years ago. Yeah.
Might be a basic question, but why do you care so much about the power that you consume? You're not using a cell phone or
Yeah.
or
Go back to the question that I showed before. Power actually, power translates indirectly to performance. Why? Because systems usually, they, let's start it a little bit backward. You get a chip, and they tell you that this chip can run 2 gigahertz. Where does this number come from? So in the past, it was the design rules that didn't allow you to go over to 2 gigahertz. Today, it is not true anymore. Today, if I take the same chip that they tell me that I can run it 2 gigahertz, and I put it in a helium, very, very cold environment, I can run it in 5 gigahertz. So from the design point of view, I can run chips way, way faster. What prevents me? When I execute something, I produce power, energy. Energy translated into thermal, and usually silicon is just sand, which we convert it to silicon, and after some temperature, it's liquid, and it goes back to something similar to sand. So there is some point that if you go over it, it just self-destroy the chip. So there are mechanisms that never allows you to go over some temperature or over some frequency. How this is terminated? By calculating how much energy you are consuming and translate it to frequency, etc., etc. So now, if you can save power, so actually you can run the system faster, even if you don't care about battery. You can run it faster because you had a thermal room in order to reach to the point that your system is too hot. Now, if you buy today an Intel turbo chip, there is something which is called turbo mode. What is turbo mode? They tell you this chip can run 2 gigahertz, but if you are not using all the 8 cores that you can use, but only 1 core, so you have extra thermal, in this case, they increase the frequency. Again, you increase the frequency because you are allowed to do it without harming the thermal point. So power translates to performance in modern systems. The last point is when you talk about farm or of computing, or you are talking about cloud computing. In cloud computing, about 30 to 40% of the cost of ownership, which is what you actually pay, is for power. So it is less expensive for a company, for the owner of the cloud, to buy expensive machine or more expensive machines, but if they save them power over the time. Because the cost of the material itself, the cost of the machines is only 10 to 15%. And the cost of the power is at least twice when you take it over the lifetime. So from the cost of ownership, it is very important. It's not the battery, but it's the cost of ownership. From the frequency, it is important. From performance, it is important. And this is the reason that modern systems do care about power and not just about performance, because there is some duality between them. Okay, so this is the main point, that in many cases optimization reduces data movement are more important than optimization of computations. I think that this is what I want to present for today, just two references to people that wants to look at this area. There is a nice book which is Deep Learning for Computer Architects that at least present the basics of the combination of how to implement efficient algorithms on existing hardware. There are an excellent set of slides which were developed in MIT, and one of the professors in MIT also works on NVIDIA, so this is the connection, but this is not NVIDIA's slides that actually go in very details about all the different aspects of implementing efficient algorithms on many different types of architectures. So if you are interested, these are two excellent references at this for a starting point. Okay, so we conclude here, and again next time you'll study about quantization, and then we go back and explain, after you understand what is quantization, how you use it in real system, why it helps, and etc. If you have questions, you can always approach me. Thanks.